All right, it's been a long haul, but we are finally ready to kick off the last session of the SEIDAS. I'm Oleg Smirnov from Rhodes University and South African Radio Astronomy Observatory. And as a radio astronomer, I'm very pleased that we have two invited speakers now who are also radio astronomers. And we're going to kick off with Eric Murphy from National Radio Astronomy Observatory, and he is going to speak about the next generation Very Large Array.
All right, everybody can hear me? Wonderful.
Yes.
Thank you very much for inviting me to talk about the next generation VLA. I think, honestly, the last time I took a trip to a conference before the pandemic, it was in South Africa in Durban. I wish I was there now in person instead of here, but hopefully soon in the future. Like Oleg said, I'm going to talk about a next generation VLA. Which is what NRAO's probably largest initiative right now. It's a new radio telescope, which will be a transformative new facility that will be replacing both the Very Large Array and the VLBA simultaneously. And the new scientific frontier it's aimed to tackle is thermal imaging on milli-arc-second scales, which for those of you who are radio astronomers knows it takes a lot of steel on the ground. The thermal sources are faint, and to detect them at high angular resolution really takes a lot of collecting area, which means a lot of telescopes and a lot of data collection. The NGVLA aims to be, or is designed to be 10 times more sensitive than the VLA and ALMA, where the bands overlap with ALMA at lower frequencies. It will achieve 10 times higher, or even more actually, angular resolution than the VLA and ALMA. The frequency range expands what the VLA can do right now in its typical configuration. So instead of just going up to 50 gigahertz, the next generation VLA will cover 1.2 all the way to 116 gigahertz. So that is accessing atomic hydrogen, the 21 centimeter line at 1.4 gigahertz, and going all the way up to CO, the lowest fundamental transition of CO at 115 gigahertz. So being able to both measure atomic gas and molecular gas in nearby sources. The array consists of 244 18-meter offset Gregorian antennas, which is complemented by 19 6-meter antennas to fill in, sort of do the short spacing array to fill in the holes left by the 18-meter antennas, as well as some of the 18 meters used in total power mode to fill in that for zero spacing. So basically, it follows the kind of how what ALMA does to detect emission at all angular scales. It'll be located centered at the current VLA site, and most of the antennas are in the existing VLA footprint, at least out to A configuration, but spread over the U.S. Southwest, or concentrated over the U.S. Southwest, and really spread across the entire North American continent. Antennas will be fixed, not reconfigurable like the current VLA, so similar to the SK and ALMA. So what the NGVLA does is really links both the SK and ALMA scientifically. So on the left, you can see what is plotted is basically sensitivity as a function of frequency. And it doesn't go all the way down to, where the SK will be at the lowest frequency end, or where ALMA will be at the highest frequency end. But the NGVLA really sits right in between these two premier facilities, and it really like sort of a final showcase or a showpiece to this next generation of suite of radio interferometers. So where the NGVLA is optimized for at 1 centimeter, it's really superb for where the NGVLA key science goals you'll see is for terrestrial planet formation, looking at the dense gas history of the universe, and baryon cycling in nearby galaxies. On the right, you'll see angular resolution plotted as a function of frequency, and this really, nails down what the instrument is meant to do. So that maroon line here indicates the angular resolution necessary to achieve 1 AU resolution. So that's the distance between the Earth and the Sun at a distance of 140 parsecs. So that's the distance of the nearest major star forming region, where there are hundreds of protoplanetary systems. And so, as you can see with this line, the NGVLA is able to detect forming planets, Earth-like planets on AU scales. on Earth-Sun distance scales. And you can see over here on the right, the ground-based large optical telescopes, the ELTs, TMT, GMT, they're trying to do the exact same thing, achieve that angular resolution, but instead of being able to detect the planets as they are forming, they're going to be detecting the planets that have already formed. So it's a very nice complement to what the OIR community is trying to do with their next generation facilities. The NGVLA project has an org chart, just showing this to make you all understand it's pretty official. We have a project director, which is Tony Beasley, who's also the NRAO director right now. Two project managers, Jill Myers and Willem Esterhaus. Willem Esterhaus used to be in South Africa. I am the project scientist. Rob Selina is the project engineer. Our system engineer also comes from South Africa, Thomas Kuzel. And we have a cost analyst, Alexia Nelvik. We have 10 integrated project teams. And the way our project is set up is to be is for seamless entry into the National Science Foundation major research engineering facility construction project definition. So that's where big facilities in the US are funded to be built. And we're looking to get to become a candidate at that very soon. And we have very active community participation through science and technical advisory councils. They've really been critical in steering the design. I think if you spoke to any of them, they would agree that they've been key members of the entire process, which I think is important. And what has made us, whatever success we've had is because of that. So the telescope is designed to really carry out a broad range of studies. Here I list them, the 5 key science goals that were derived based on a use case capture from the community. Over 180 of individual observations were captured by community members. We gave them basic instructions. What would you do with a facility that had 10 times the sensitivity of the VLA and maybe had frequency coverage up to 116 gigahertz? And we got a broad range of responses, which really shows that the community, at least the US community at large, really wants a telescope that they can dictate what the project is. Not a survey style telescope like LSST, but something where they can carry out their own investigation. So the 5 key science goals go from unveiling the formation of solar system analogs and terrestrial scales, something I already mentioned, probing the initial conditions for planetary systems and life with astrochemistry, something that's also uniquely done at sort of centimeter and below frequencies, charting the assembly, structure, and evolution of galaxies over cosmic time, using pulsars in the galactic center as fundamental tests of gravity, and understanding the formation and evolution of stellar and supermassive black holes in the era of multi-messenger astronomy. So yes, very broad, a disparate set of science goals, and the design of the telescope has been set to achieve each of these science goals. So the first one is unveiling the formation of solar system analogs. So on the left here, you can see the pretty famous image of H.L. Tau showing rings around a protoplanetary disk. Below, you'll see a zoom in. It's a simulation of a solar system-like, sort of a Saturn, Uranus, Jupiter, and Neptune mass planets forming around a solar-like planet. This was done by Luca Ricci to show you what the NGVLA will be able to see. And given the number of systems that will be available to the NGVLA, there'll be somewhat of hundreds that have orbital periods of less than 10 years. So this image this animation to the right shows that not only will we be able to study these protoplanetaries statically when just making images, but we'll be able to revisit them over time and watch the planets form in situ, in real time, which I think will be an absolute game changer in the studies of planet formation. And the image in the middle just shows what's achievable in the numbers given the number of known planetary systems that could be detected and resolved by the NGVLA compared to what ALMA can do and the future ELTs and what is currently done now with existing telescopes. Another key science goal, I'm not going to go over all of them, but another one is charting the assembly and structure and evolution of galaxies from the first billion years to the present. So the NGVLA frequency coverage and sensitivity allows us to measure low J transitions of CO over at all redshifts. And why this is important is because by accessing the low JCO, you trace the bulk molecular gas of galaxies, which is a qualitatively different picture of what you get with existing element observatories when you measure the higher J transitions. So the higher J transitions really trace the warmer, dense gas, while the low J transitions trace the bulk colder gas. And this is shown in this simulation up here. So on the left, you see a simulated image of ALMA. The CO, the transition is J equals 4 to 3, which is really showing you just the center of the gas, where all the action's happening, the warm gas that's actively participating in star formation. In the middle panel, you see what the NGVLA could do with by accessing the J equals 2 to 1 line. So you see more diffuse or cold molecular gas surrounding the central star forming region, but for the most part, it's pretty centrally concentrated. In the right, you see what NGVLA will pick up by going and detecting CO equals 1 to 0, which again is a qualitatively different picture of what you get with ALMA. So if you wanted to know what the bulk, how much molecular gas are in these galaxies at high redshift available for star formation without having access to this low J line, it's almost impossible to figure out. And then the last one, key science goal I'll go over is that of understanding the formation and evolution of black holes in this new era of multi-messenger astronomy. So the NGVLA will be sensitive to black holes of all masses. We can have searches in the galaxy, largely followed up by some other sort of observational tag and go in to see if we can detect any accreting black holes, again, of all masses. But the really cool thing, I think, is that with the long baseline, the very long baselines of the NGVLA cross-continental baselines, we'll be able to, unaffected by dust, have the sensitivity and the resolution to resolve dual AGN and black hole binaries. And with the sensitivity available, measure proper motions over 5-year periods of expanding jets from these potential gravitational wave sources. And this is shown in the plot on the right, the projected nuclear separation of the sources as a function of redshift. And this orange area shows you exactly where the NGVLA will be able to have the sensitivity and the resolution to look at these expanding kilonova events from gravitational wave sources. So I think that's super cool. To date, we've had strong community participation, both in the US and abroad. This is a smorgasbord of logos. You'll see in the left, mainly US institutions. We have interacted with the private sector, industry, and then a number of international partners who all participate either on our advisory councils, through our community studies program, as well as our technical advisory councils. To date, I think we've been pretty successful at community engagement. Of course, that looks a lot different now than it did a couple of years ago when we were having more in-person meetings. Hopefully, we're starting up on those in much more full force soon. But even through COVID, we've been pretty successful at hosting Zoom short talk series over the past couple of years. We've run our community studies program, which has been extremely successful, where we go out to the community, both international and in the US, and ask for people to look into different areas that either we don't have in-house expertise or don't have the person power to conduct such studies. I mean, one example is RFI studies. In South Africa, EMSS has been helping us with our receiver feed studies and our optical design efforts. We've also hosted a number of NGVLA town halls, and I think we're doing the best we can with what we got, and I think because of that, we get pictures like this, which contain many people who I don't usually see. I mean, a lot of times when I was going to radio conferences, it was all the same people, but I think we're very similar to the SK, able to generate. We're getting a younger, new. Early career group of people excited about the telescope. International engagement has been ongoing since the beginning. The members we have a group of international members that participate in our science and technical advisory councils. This includes Canada, Mexico, Japan, Germany, Netherlands, and Taiwan. Right before COVID, just before this, the meeting, I was in South Africa. I was in Japan for our first international science meeting in Mitaka, hosted by NAOJ. The Japanese right now, actually just a couple of weeks ago, released their own NGVLA science book, which is completely in Japanese. They have their own website, and they are being considered as the NGVLA is being considered as part of the Japanese Master Plan in 2023, which is similar to this U.S. decadal process, where a bunch of presumably very smart people set the priorities on where government should fund money for science. And also for the Canadians, they just went through their decadal sort of process, the long range plan. And the Canadian, the recommendation there was to be a 6% partner in NGVLA, which is exactly the same percentage I think that they are for SKA. So what does the instrument look like? The technical baseline is here. Frequency coverage, like I said, 1.2 to 116 gigahertz. We have a main array of 214 antennas, which are spread across the US Southwest. About 75% of them are within the existing A configuration of the VLA, and the rest of those then are sort of spread out to 1,000-kilometer baselines into neighboring states in Mexico. The short baseline array that I already mentioned, and then we have a long baseline array of 30 18-meter antennas, which fill up the existing VLBA sites and plus another few. There are 3 antennas at each location, so giving us the full VLBA cross-continental baselines of up to 9,000 kilometers. Here's some images on the distribution of the antennas. You can see to the left here, the US Southwest. Then we have this 5-arm spiral here with a central 4-kilometer core. This then expands into 5 other arms, which go into the neighboring states. And then up here in the right, you'll see these purple sites. These are all the long baseline sites. They're sort of paired for phase calibration purposes. We tried to keep them within sort of 1,000-ish kilometers of one another. So that's the reason for that. The antenna concept, here is the current design by MTEX, who we've contracted out now to build a prototype. It's a feed load design like the SK for maintenance requirements. We have a mount concept and well, I guess we lean towards still pedestal. We're going with the pedestal concept. Direct drive motors and traditional panels with steel and bus and composite reflectors. Right here, you'll see key specifications of the antenna: 18-meter aperture, shaped optics, a surface RMS of 160 microns, 4-degree slew and settle time in 10 seconds, reference pointing of 3 arcs second RMS, and then, like I said, offset Gregorian design or optics. So then you'll see this, they're designed with their little Mercedes down there. The front end concept is 6 bands and 2 dewars. The 2 lowest bands are Y bands, 3.25 to 1 bands, quad ridge horns. So the L band is 1.2 to 3.5 gigahertz, and then our sort of C-ish the CS band is 3.5 to 12.3 gigahertz. The middle 3 bands go from 12.3 to 50 gigahertz, using sort of standard corrugated horns to maximize sensitivity. And then for the band 6, the highest frequency band, we also use corrugated horns with waveguide LNAs with lockdown conversion. For cryo cooling, right now we're doing a 2-stage Gifford-McMahon system, but we're also still looking at a Stirling cooler situation or a solution. There's a trade study out for that, but right now we're sticking with the standard GM cooling. For software and computing, so the operations concept is a science-ready data product telescope. So each observing mode, standard observing mode, the user will submit information via the proposal, which would set up, the observations, and also dictate what the high-level data product that needs to come out of the telescope based on those observations. And that's what the user will get at the end. So this is both for initial observations or archive projects which reprocess existing data. For post-processing, so the analysis shows that storing all the raw visibilities will be tractable when NGVLA goes into operations. Data processing is post facto with a system size for average throughput. The average data rate is just over 7.5 gigabits per second, designed for a peak of 320 gigabytes per second, peak. So a 4-hour observation will generate about 110 terabytes, and it requires about 1,000 cores to process in a few days. So the computing expectation, right, is about a 2 billion core hour problem, which is challenging, but can sort of, but the thought is can be met with an off the shelf solution cluster. This sort of computing is throttled by time resolution, spectral resolution, and multifaceted imaging. So the way we get away with keeping visibilities and not blowing up the compute is we're not going to allow some low frequency full beam AW projection cases. So we're not going to allow basically the fringe cases, the observing cases that completely blow the compute budget and the data storage budget. And we'll wait for technology to catch up there. We've been busy over the past year. So for FY21 activities, we hosted a special session at the AAS. We've carried out the community studies that I mentioned. There were 7 approved and 4 funded in the US. The biggest news for sure is being awarded $23 million from the NSF for the antenna development and the prototype. We're really working hard to get through a conceptual design review next year to be MRAFC ready for the NSF. At that point, all the requirements will be baselined. As I said, the award went to MTEX to do this final design and prototype, and we're also ramping up on the preliminary design of all major systems at the same time. High-level goals right now, I'd say the number 1 is to be ready to react to a positive ASTRO 2020 decadal survey outcome. That is to be released next Thursday that we just found out, which is exciting. Obviously, everybody's probably a little tense, but we're hoping for a positive outcome. We want to continue to advance the NGVLA conceptual design so we can get right into that MREFCQ at an NSF. We're going to continue to build and work with the community to hone the science case, finalize the antenna design and prototype, and we're starting to really formalize international partnership. We just had a meeting yesterday morning with potential partners to start to talk about plans post-decadal. And then once the decadal comes out, we're actually going to have to start to look at what the VLA to NGVLA transition plan really starts to look like. And to do that, I think it's going to be led by a community-led working group. We'll carry that out hand in hand with NRAO. Project timeline, this is what it looks like. So we submitted to our project to the ASTRO 2020 decadal survey, which seems like ages ago, and I guess it was back just after 2019. We have the recommendation will come out on Thursday. After that, if things look good, we're going to be ready to submit a proposal to the NSF to become an RFC candidate. With the current antenna schedule, the prototype will be delivered to the VLA site sometime in 2023, which is very exciting, and then fully vetted and validated probably by 2025. We hope to come out of the NSF, the MRAFC with the final design review right around 2025, and then kick off construction. Early science operations should start sometime in 2029, and then full operations, thank you, in 2035. So perfect timing. So to summarize, community engagement continues, and I think it's only going to increase. If things go well, we're going to be looking to get the community even more involved. Oops, sorry. By various activities, basically observation planning and thinking about key projects. Project management systems engineering is ongoing, and that's ramping up too. We're really working on our conceptual design packet. Industrial and international partnerships are ongoing and building, and very excited to say that we will have an antenna on the plains of San Augustine in 2023. And this has really all been made possible by significant financial support by the National Science Foundation. So happy to take questions now. Thank you. It's nice to hear real clapping.
Yeah. Thanks very much for a fantastic talk, Eric. This looks awesome. And I'm glad to see you're hiring so many South Africans. Shows you're really serious about this.
Clearly, there are a couple more in our heads too.
We have some questions on Discord. I think the first question is from Peter Tubin. Did the simulations incorporate short spacings? And what's the current thought, how and when the short spacings are observed?
Which simulations? For the planet formation? I guess you don't know. So we actually, we have an NGVLA memo series where we've gone through and carried out the exercise of what the image fidelity is with and without the short baseline array and total power. So we do have those simulations. Whether or not that they're taken simultaneously, I think the current thought is that they don't need to be. The short spacing array will be working on its own, separate from the main 18-meter telescopes.
All right, thank you.
Unless someone requests it, especially, right? Unless there's a scientific reason to do it, simultaneously.
Okay, we have a question from the audience. Landman, you want to take a microphone?
Hi, Eric. Thanks
Hi.
for a great talk.
Very well.
I was wondering, how worried are you about RFI and space junk ruining your key science goals?
Yeah, so that's a very good question and something that we are, been actively working on, concerned about. So we have a new RFI sort of task force in-house that is looking at the impact of SpaceX, where SpaceX has actually thrown some money, our way to help to diagnose the impact of their Starlink. And we actually even have some of the uplink things at the VLA site, and we've been testing that over the last month. I mean, so far so good. They don't seem to be blasting away too hard. I think it's what you think it is. If you point at them, you're going to see them. If you don't point at them, it seems a little bit harder. But for the most point, right, interferometry helps us with this, and the longer baselines helps us with this to sort of avoid that interference. So I think we're not, while a concern, and we don't want to give up any sort of frequency space that we don't have to, I think we're feeling like this is a manageable problem.
Thank you.
We have a question from Francois Bonnerel in the chat. What kind of plans for that data archival and open distribution?
Well, that's a good question about the open distribution. We will be running an archive. Exactly what that archive looks like is TBD. But the current thought is that, as I said, raw visibilities will be stored. One can reprocess them. They'd have to propose for it. It's unclear, what the compute cost is there and how frequently we can do it. The high-level data products will be stored so people could access. In terms of, there will be a proprietary period, I'm sure, of a year standard that what we're doing now with current NRAO facilities. But that is a good question. There's even talk of whether or not, partners might come in and want to host their own archives, or we do something distributed. But I don't see there not being some sort of a centralized archive that is run by us.
All right, final question perhaps from David Buckley in chat. What do you consider the most compelling joint science programs that NGVLA and SKA might work on together, which maybe neither could optimally do on their own?
God, that's such a good question. That's a good question. It's hard for me not to go back to my bread and butter, but with a lot of the large area mappings for the extragalactic sky and these tiered surveys that the SK will do, and spend a lot of time on them. For the galaxy evolution studies, going in and taking that statistical information and tying it with the detailed studies of individual systems, both the gas and star formation properties, I think that's going to be a powerful tool for constraining the formation and evolution of galaxies at very high redshift. The SK will see a lot of, because of their large area maps and depth, they're prone to find a lot of new and exciting exotic systems that the NGVL will be very keen to follow up. And if I studied protoplanetary disks or something, I'm sure I would say something different.
Great, thanks very much. We're out of time, but further questions can be taken on Discord, Eric.
You got it.
Let's thank you, Eric, again. And continuing with radio astronomy, our next invited speaker is Urvashi Rao from National Radio Astronomy Observatory, and she will speak about uncertainty quantification in radio interferometric imaging.
Hello, everyone. Thank you for joining in today. This talk's going to be about defining correctness of scientific software and how this generally plays out in the field of astronomy, and in particular radio interferometry. So let's start with a picture. This has been taken from the book referenced at the bottom. It shows what scientific software generally is. There is the real world, and then you have to make a bunch of simplifying assumptions and approximations to form a mathematical model of that world, which is then encoded with a variety of discretization and algorithm choices into a computational model, which is then implemented on computer hardware using software. Okay. So at every stage, there are assumptions and choices being made which deviate from the real world. And that's what contributes to what we call accuracy or error. Now, of course, in astronomy, we are making images of unknown structures. And so there is no known absolute truth in general. And we are using instruments whose characteristics must be modeled and corrected for in the software. In real life, what this translates to is questions about what defines the absolute correctness of an end result. How much can we trust it? Then what defines the operational readiness of the software? Because given the understanding that there are going to be differences and errors, how good is good enough? And finally, as software and code evolves, what does one do when numbers change? What can you trust and what can you not? So there are a number of standard development practices, and all of them talk about requirements, specifications, and tests. And at the core of writing a test or a requirement are these two things. You have to have a truth value that's known and understood and accepted. And you have to pick a tolerance which can encompass any of these different criteria against which you can compare your output values. Okay, so let me say a little bit more about truth values and tolerances. Truth values, in our case, where we are observing something unknown, can come from simulations, where in this case, it means making a model of what you think the sky is and simulating a controlled environment and producing a data set that you then take through your standard data reduction process. So a simulation essentially lives in this mathematical model space, and it tests the rest of the system. Now, you can always also use a test observation, which of course is much more realistic. It comes from the real world. But the caveat is that you're not going to have a knowledge of absolute truth. You could use an independent measurement from some other telescope when available. But in reality, it turns out that what one uses is just the value obtained whenever the test was written as the practical approximation of what truth is, given a human evaluation proving that it's good enough. So these are about truth values. What about tolerances? There are a lot of options to pick. You could pick an accuracy needed for the astrophysics, which is a real world metric. For example, what is the error bar that I can tolerate on a certain measurable so that you can distinguish between two different theories, for example. You could also pick an accuracy defined by the instrument's limits, which is the best case scenario for a given instrument and observation. Usually the astrophysics limits and the instrument limits are defined beforehand in conjunction with each other, but sometimes they can be different. You could also pick the accuracy of the algorithms and implementations themselves, which means leaving out the real world and just quantifying how good that, given your mathematical model, how good does the rest of your system compare, assuming that your mathematical model is real truth. So that's what that metric is. You have to factor in where machine precision comes into play, and when it makes sense to use machine precision levels as your threshold and when it does not. And of course, all of this has to account for the effects of error propagation. So given so many options, the practical reality that comes to play is that when code and algorithms evolve, your numbers are going to change. And you're going to end up with questions of what changes are okay and what are not. Which kind of tolerance to use. Sometimes your best result truth values can change as your algorithms improve. And sometimes you have a bug which mimics the effect of a legitimate real world to model approximation. Now, obviously, if there's a bug, it must be fixed. But in some cases, if it's not really a bug, but it's a difference due to legitimate choices that you have to make when converting a real world model into a computational, reality, you can end up in a situation where you reach the point of diminishing returns and you have to start asking the cost benefit question of when is it worth it and when does it matter. So all of this comes into play in real life. So let's get into a bit of a case study. I want to describe radio interferometry and how all of the sources of uncertainty play out there, and how the CASA software package attempts to navigate the situation. So radio interferometry, for people who do not directly work in it, is an indirect imaging technique. This means that we do not make images of the sky brightness directly, but we make measurements of the two-dimensional spatial Fourier transform of the sky brightness. It's an incomplete sampling. We assume that a measurement noise is Gaussian random. And our reconstruction process is an inference problem. It's an iterative numerical optimization, and it solves for, in different stages, parameters of both the instrument and the sky model. So in pictures, it looks something like this. You have a set of antennas and receivers, and signals taken from all of them are correlated, and there's a set of signal processing with their own quantization and assumptions in there. The data set that comes out of this goes into an archive and is then taken for post-processing. Now, post-processing is where we're going to focus our attention today. And there are three main steps of post-processing. The first is what we call flagging, which is essentially just identifying and masking out corrupted data. So there are a couple of ways in which flagging affects the error budget. The first, of course, is data loss. Since you are identifying and throwing away some data, the amount of data you discard is going to affect the best possible outcome from that data set and the theoretical noise limits and such. Flagging also involves outlier detector algorithms, and so you now have to contend with the accuracy of those algorithms. The next step is generally calibration, where you have to solve for and apply corrections for instrumental effects. Okay. And here also now, this is an iterative solver, and there's a model of your instrument that is approximate. And so you have to account for the discrepancies between that model and real life. And of course, the available signal to noise to allow you to even get a robust solution. The third step is image reconstruction, which is again, iterative model fitting while correcting for some other instrumental effects. And so here too, you have to contend with various approximations in the models being used, the uncertainty of the reconstruction process itself, since we are do an inference problem because of incomplete sampling, and also the fact that there needs to be enough signal to noise to get a robust solution. So all of these contribute to errors. Now, an actual data reduction sequence is not just 3 steps. It looks more complicated, where there are usually a variety of flavors of each step interspersed within each other. And for example, this picture here shows what one of the instrument pipelines implements. It's a whole sequence of steps. There are feedback loops, conditionals, and all kinds of heuristics implemented in it as well. And so if you're looking at the output from a pipeline like this, you now have to also deal with the accuracy of the heuristics that have been developed on some data sets and applied to others, and the effects of error propagation. So putting this all together into our favorite picture again, you have the real world. In this case, it's just the physics of the incomplete sampling of the data domain. You have the instrument system noise and the amount of data that you can keep or lose. You have all of the models that you put in, which are the simplifying assumptions. For example, you model the sky distribution with a bunch of delta functions or wavelets, which is an approximation. You model instrument parameters differently, and you make an assumption that your noise is perfectly Gaussian. When you're implementing an algorithm, the discretization comes in. And for example, it's how do you control aliasing errors? Or what are the pixel or bin sizes you choose for various things? And of course, the algorithms themselves and how much you allow control for them. You then have to run this on different kinds of hardware, because hopefully your software is going to outlive system libraries, and you're going to have to keep updating things and changing parallelization approaches as your requirements change. And so you're going to start to see differences simply because of this part of the problem. There are, of course, going to be bugs, and you have to contend with the effects of error propagation. Okay, so this is how this is an example of how all these factors play together in, say, radio interferometric imaging. So how do we deal with this? First of all, what is CASA? CASA stands for Common Astronomy Software Applications. We are a general purpose suite of radio interferometry analysis tools operable within a Python environment. And we put out 1 to 3 releases per year. We are a team of about 20 people, a mix of software engineers, algorithm scientists, and astronomers. Our stakeholders are mainly the VLA and the ALMA telescopes, although people from other telescopes also use our software. In recent years, there have been pipelines developed on top of CASA for the VLA and the ALMA telescopes, and they are some of our dominant stakeholders. And more recently, the NGVLA telescope, which is hopefully going to appear in the next decade, it has also begun using our code for some of their tests. We partner with an algorithm R&D group, a pipeline development team, and several other associated teams for parts of the development. And I should stress that the production pipelines, which a lot of people hear about with these telescopes, are built using CASA methods with heuristics by a completely different team. What we are talking about today is just the building of the library and the tools which are used by these science application teams, so to speak. You can get a feel for the size of our user base from this plot of the number of unique monthly users of the software obtained by telemetry measurements. We follow a pretty standard development process involving requirements, specifications, verification, and validation. And the parts in the red box here are what the core team is responsible for, and we interact with the science application folks on either side of the process. So where does numerical accuracy come into all of this, and how does this play out for us? To get there, let's talk about the operational complexity that we work with. We support a variety of usage modes. There's manual data reduction, where people interactively use the software. This is where people are exploring how best to reduce their data. So the emphasis is on flexibility, with a lot of parameters and options to tune and explore the algorithms. And this is also where a lot of new options and features are always being added. So the code is in flux and the code is changing. We also have production pipelines that we support from the same code base for multiple telescopes, and they have slightly different needs and requirements, but they all require stability and reproducibility of the results. They do sometimes require algorithmic evolution as the pipelines introduce support for new modes, but they also have a very, very low tolerance for unasked for changes. We also have to support algorithm R&D, which is more of a software design aspect and less of an operational one. It's about modularity mainly. But this is the range of use cases, usage modes that we support. We have to operate on a variety of platforms ranging from desktops and laptops to cloud operations and different types of parallelization schemes. Our code base is predominantly C++ and Python for now, and we are experimenting towards moving to a more Python-centric ecosystem. Requirements are usually written as feature requests, algorithms, or problems to solve. And metrics are not often defined upfront. They're usually based on the best possible outcome after experimenting with the solution. And so often metrics and tolerances are defined post facto, not at the beginning. Sometimes independent analyses are available to do so at the beginning, but they're not always possible. And we have to contend with and live with that reality. So if you put all of this together, there's a lot of complexity with somewhat competing requirements. For example, you need to be able to constantly add features to the code and provide flexibility and tunability, which means more options for bugs as well. And you also have to be extremely stable for production pipelines. You have to evolve as the systems and architectures and operating systems change underneath you. And the numerical changes that come just because of this sometimes also get us into trouble because of the low tolerance for unasked for changes. The fact that metrics aren't always defined upfront, because sometimes it's just not possible. Your truth values keep changing based on your current output from the software. And so when the software changes, all of that has to be re-evaluated again. And so in the end, all this put together, people have generally become extremely wary of change. There is a certain degree of loss of objectivity in evaluating when things are acceptable for operations or correct or not. And this all leads back to a very inefficient development process. And so we are actively working on various ways to build trust so that we can improve the situation and make it more productive. So one obvious way to build trust is tests. And so we're increasing the test suite. We have a variety of tests, test types. There are what we call functional verification tests, which are the basic tests written against feature specifications, and the emphasis being code coverage. And they usually use small and simple simulations of data sets and test the basic features. So this is essentially testing the right-hand side and looking for regression and whatnot. You then have algorithm characterization, where we, on certain topics, go into much more detailed simulations and analyses using science metrics, and often compared with independently calculated metrics. If you have simulations, you have truth values to compare with. This essentially tests these the bottom and the right side of this diagram, which is assuming your mathematical model is a true representation of reality, how good are your algorithms and all of your implementation choices for solving that situation? That's what this tests. Then we have more real world tests, which we call stakeholder verification tests, where for major usage modes, we have actual real data sets. And in this case, we use analyses, steps, and metrics relevant to the different stakeholders. And this is the place where we also track differences and changes at numerical precision level, which gets interesting sometimes. There are also pipeline validation tests, which I should emphasize are not run by us. They're run by the science application groups. And they test end-to-end analysis runs. And that's where the error propagation tests come in, metrics come in. There are also performance tests. And of course, there are also manual tests where people just use their own experience and technical expertise to judge whether something is correct or not. So all of this has definitely helped in improving the trust in the software. But there is still a large variety in the metrics, tolerances, and general acceptance rules. And we often run ourselves into loops trying to navigate this with a whole range of stakeholders with differing interests. So one of the things we're trying on this run is to try to go towards something consistent in terms of metrics as well. So again, this is not unique. These are some of this are pretty standard in other areas. We are hoping to at least pick some major usage modes for different telescope operations and get science-driven accuracy limits defined upfront. They could be in the form of requirements versus goals, where requirement is whatever is good enough for most operations, and a goal is what's the best case scenario. And this is also the algorithm development target. Along with this, we have to also demonstrate the numerical and absolute limits of the software given ideal data. And this is where the accuracy of the solution for an idealized mathematical model, how good is that? And that's what we may call a Z over here. And for this, we may use simulations or carefully designed test observations with definitions compared with results compared to known truth values. And now for a given use case or a usage mode, once you have these three numbers, in principle, it is possible to define clear acceptance rules. If, of course, your documented spec of the software is tighter than what's required for both the requirement and goals for the science, and this is clearly above the numerical precision level of your machines, then all is well. If, however, what your software can demonstrate is larger than, the errors are larger than what you need for any science, of course, that's unacceptable, and it needs algorithm R&D or a reevaluation of the requirements. The gray zone is the more interesting, where if what your software can do is good enough for most operations, but not good enough for everything. So it's acceptable, that means you can operate, you need not block operations, but improvements are obviously desired. And this is the gray zone where one gets into the state where you need to now track changes and understand every little change. Even though it may still be acceptable, you still need to know why the change happened, and things get interesting and have to be done on a case-by-case basis, but there may not be a way to get out of this. And the goal here is to at least constrain this extra effort of detailed bug tracking and analysis to be only for the situations where it really matters and not for everything. The other side effect of this is when numbers change, what do you do? The hope is that we can use the tighter constraint, tighter of Y or Z, which is the best case for this use case, or what is the best case by the software. Pick the tighter of the two, and maybe use that as the tolerance for acceptance when numbers change due to unrelated reasons. I mean, by unrelated, I mean you change an operating system or change a compiler and the numbers change slightly. It's those kind of things. And basically to allow the code to evolve within these limits. Now, of course, there are pros and cons to this, and you might have slight bugs which cause differences only below this threshold. And yes, some of them may live on, but there is a compromise to be made. So this is what we are trying. We haven't fully implemented this yet, but we are trying this out for a couple of ongoing development topics to see how it goes. So going forward, for current operations and support of the ALMA and VLA telescopes and the various surveys and pipelines, we have to continue as is. And we will be working to define metrics retrospectively and try to evolve the way people view the correctness of the software. For a new telescope, that is the NGVLA, and upgrades to existing telescopes such as those planned for ALMA, we are most likely going to require a new software package, and work has begun on prototyping this. But here's an opportunity to define all of this correctly upfront. And so since we haven't started yet, we can theorize. And so let's assume that we can define clear use cases, metrics, and get acceptance rules decided upfront. From experience, we know that it is not enough to just do this once. And so the model has to also allow for evolution. And this situation is not different from any of the other new telescopes being developed by others in this field. But so we also have to do the same thing. At the same time, we are also evaluating what we're calling the CASA Next Generation Infrastructure project. And this is a move towards more open source third-party infrastructure to give us more operational flexibility, and even for some numerics. What this means in the context of numerical correctness is we might end up with reduced in-house control of numerics, which makes it even more important for us to get these use cases, metrics, and acceptance rules sorted out at the start. Otherwise, this is not going to get off the ground. So we'll see how it goes. But that's basically how our project is trying to deal with and navigate this situation. Okay, so that's all I have. I'd like to end by perhaps inviting some discussion. If there are other telescopes and projects who have successfully navigated this whole issue, not just at the start when an instrument and a piece of software is new, but also as the system requirements and instrument evolves. If you have tips and tricks, please do consider sharing them with the community and us. And for everyone else who has perhaps not gotten a chance to think about this entire scope so far in this level of detail, I hope that this has provided some food for thought. Thank you very much for your time.
Thank you very much. And I'm sorry I made a mistake in your title. I just had a brain fade as I was introducing you. I see you've already answered the question on Discord, and we have more questions coming in. Peter is asking, in CASA, are all steps basically MC-able? In the sense of Monte Carlo, I guess?
Yeah. I guess yes and no. I mean, you can run them, they're parameterized, but it may not be advisable to do so from a runtime point of view. The information that you would need to retrieve back is probably not going to be consistent enough. But from a point of view of just methods that you can run with parameters, yes. I hope that vague answer was okay.
Okay, and we have questions in the audience here. I see there's Space I'm going to ask a question if he wants to ask it live. Lanman will ask a question live. Just a second, he's coming to the microphone.
Hi, Urvashi. Thanks for the very nice talk. What I want to know, so in the development of the potential NG-CASA, are you planning to move to a more modular structure? So if I only wanted to use some tools in CASA but didn't want the entire, say, half a gigabyte of binaries. Would this be possible?
Yes. In fact, we are even evolving current CASA to be more usable in that way. And in fact, some of the later releases have separated out what we call tools and tasks and different things separately. But going forward, we are looking at even separating things out even more into functional blocks that you should be able to call. So short answer, yes.
Okay. And just one more question, if Oleg allows me. Also, like in terms of developing these metrics and I suppose an implementation eventually, will that be housed in CASA or will it be a standalone project that can be accessed outside of CASA?
I don't have an answer for that. Right now, we are just trying to get it going within CASA. But the concepts of how you define these things have to be done along with the science teams. So we expect to have a set of documents which will, live documents, which will always maintain the current state of what are the use cases being supported and what are the metrics that are being used, and also how well are we satisfying those metrics or not. So some live summary of that we will hope to always have once we have this in place. And that hopefully will be accessible to the external community as well. I mean, this can be made public. So one example of this that we're trying right now is just for a specific case, is as simple as just making a Jupyter notebook that you can take from the CASA documentation as an example, run it on Colab, and have an example of what the code can do along with metrics and outputs. So we are putting together such things. That's an example for one feature. How we do this for everything, we haven't gone through the details of that yet, but I think your point is when there's information about the accuracy that is documented and how it fits, is that going to be publicly available? And I would hope so.
Okay, cool. Thank you.
Thank you. And we have a question from Landman now, live.
Hi, Urvashi. Thanks for an excellent talk. I'm happy to see that other people are thinking about these things as well. And I'm sorry if I missed this. Maybe I drifted a little bit. But when you define your quality control metrics, how do you actually do this without uncertainty estimates? Because as you say, it can come from a number of sources. Like incomplete UV coverage contributes to, you won't be able to reconstruct your model perfectly because of just that. On top of that, you've got noise. On top of that, you've got calibration errors. So if you don't have uncertainty estimates, how do you come up with quality control metrics and how do you sort of enforce them?
That is exactly the question that we are also trying to figure out. But you can separate them into two parts. So there are some parts which you can calculate. For example, if you know the noise thing. So if you know your input noise, number of data points, and how you're stitching together mosaics and things, you can predict noise levels and compare against them. The reconstruction uncertainty is the nonlinear part, and that you pretty much cannot with current algorithms. So there you go by empirical estimates. And so you either go by experience. So you say, okay, for all VLA data at L-band, empirically, the best accuracy we've ever gotten or seen on spectral index is 0.1. If I pull a number out of a hat like that, based on experience, you then set that number. But a more rigorous analysis is going to be dependent on the data set. And so it's hard to make a generic number. So that is going to be difficult. There's no easy way around that. The best thing I think we can say is, for the parts where you can predictably calculate, like noise and number of data points kind of thing, one should definitely do that. Use experience and model your experience as a metric and put numbers from empirical numbers for the parts that you can't directly calculate. And at least you have these two numbers in hand now, and then weight them appropriately and work with that. At least that's a theory. Let's see. Do you guys have any better ideas or solutions on this front, since you've also been thinking about it?
We have some, but none of them are implementable in Hubble time.
Yes, exactly. Monte Carlo ways are, of course, you can test for everything. But, yeah.
Thank you.
Great, thanks very much. We've got some more interesting questions in chat, but we're now out of time, so I suggest we take the discussion to the talk channel. Let's thank our speaker again. And next up, we have Frosi Economou, and she is going to speak about the Rubin Science platform on Google, the story so far.
All right, hello. I've been convinced that if... All right, hello. I've been convinced that if I record this, I get to have fun answering questions on Discord. So there better be questions on Discord, or at least statements, or at the very minimum, in-jokes. So I'm here to talk to you about our work deploying the Rubin Science Platform and a number of our other services on our interim data facility on Google Cloud. Credit to Will for doing all the work, like writing the slides and writing the paper while I was whining about how busy I was. You can tell they're Will slides because they're not in dark mode. All right, let's go. Lots of teams represented in the work referred to here, and very grateful for all of their efforts in contributing to this great enterprise. Rubin NLSST, the Legacy Survey of Space and Time, as we have acronymed the original name to. Big survey, 10 years, whole sky observed every twice a week from Sarah Pachon. Image of the field of view compared to the moon. We take one of those every 20 seconds for 10 years. There's going to be a lot of data. Very exciting project, and we're very happy to be nearing the finishing line, or at least the starting line for it. So the interim data facility, the IDF, and how it came about. We started the construction with one data facility at NCSA. Things changed in the funding landscape, and there was a search for a new data facility for operations that was going to be based in a Department of Energy lab. For a while, we did not know where that was. This was creating a lot of uncertainty. There's, of course, schedule risk in kind of pivoting a whole on-prem data center on that timescale. And so we decided, and our management supported us in setting up our data facility on commodity computing, specifically Google Cloud, and using that as a way to just keep going while the US data facility, which has now been awarded to Slack, gets underway. Very important to note that this is not a proof of concept, it's not a cut down kind of experiment, it's not an MVP, it's not a toy, it's not practice. This is an actual production facility. It's actually the most production facility we have because it's the only of our deployments that actually servicing external users. This is an honest to God high uptime environment. We don't take it down for maintenance. We preserve service continuity, and we take it very seriously and really treating it as a real production environment. And it has been a very good experience. We got going very quickly after we signed the contract and have been able to really do quite a lot with it so far. The architecture is reasonably complex because it's a complex system. There are many clusters dedicated to Science Platform and processing and the high-performance database. I'm not going to take you through the whole architecture, but I do want to kind of point out some kind of notable things. We don't use the Google console to set up our infrastructure. We are entirely kind of bought into infrastructure as code. We use Terraform to configure all the computer resources that the production clusters use. That way we get reproducibility, we capture configuration, we can tear things up and bring them up again, and basically practice infrastructure as code. Most of the services are running in Kubernetes. In the case of the Science Platform, they're also managed by Argo CD. Only developers are infrastructure accounts. You don't need a Google account to use the system. In fact, we don't encourage you to do that at all. The Science Platform has its own authentication authorization system, which currently is being backed by GitHub Auth, since a lot of our users already have that. That is obviously not the end game operationally. Data access is through our Generation 3 Butler, which has now finally hit prime time. We're in the process of deprecating the Generation 2 Butler. And in the case of the interim data facility, the the data stores backing the Butler service are on Google Cloud Storage, Object Store, and the POSIX file systems are backed by Google File Store. We have many other deployments of the Science Platform internally, including at the Telescope Summit, and we have used a number of different ways of backing these. So there's no kind of lock in here. It's just a choice. It's particularly well suited to this environment. And our own high-performance database layer is also deployed in Kubernetes. That's QServe. We also use the commodity database service, which is Cloud SQL for Postgres, for relational access for services that need it, like the Butler. Our data preview program is intended to both do an early release of services that are already ready, even though we have not actually reached first slide yet. It's intended to bring on an early kind of slice of the community, including underserved users, to gain experience, give feedback, and allow us to kind of get our materials ready for them, see what they do, guide us in our priorities for development. And so that's already started. Data Preview 0.1 was launched in June. It went staggeringly well, really. And I've jinxed it now, haven't I? It's about, 250 users, which is, respectable, but of course it's only a drop in the ocean of the 10,000 users that we eventually expect. Kind of keystone to the user services is the Rubin Science Platform, and this is an entire data side set of services that allow users to interact with data without having to download the petabytes of data that are involved. And so it involves a web portal that is backed by the Firefly team, the notebook aspect backed by the Square team, the API aspect is the VO services that we are currently ramping up. I should point out the notebook aspect does give you access to a Unix command line, so you can do pretty much anything at that point. For DP 0.2, we are once again going to use simulated data provided by the Dark Energy Science Collaboration, but this time, instead of taking the data products as is and just publishing them through our science platform, we are now going to put those data products through our entire data processing infrastructure, process them ourselves. That gives us data with the actual final data model that we expect from our own data, gives those teams an opportunity to rehearse their processes and services. And we're hoping to be online with that in June, so a mere 1 year after DP 0.1. And after that, there is Data Preview 1 and Data Preview 2, which are going to be with actual Rubin data, because we will have that on Sky by then. Pandemic and global catastrophes permitting. It's been really good getting real human beings, not that in-project users aren't real human beings, I hasten to add, but it's been really good to get external users on their services and to see how they're doing. We have a community engagement team that has been very good at supporting those users with tutorials and example notebooks and so on. And we are learning things along the way. Some of them we kind of expected to learn. Some of them have been more of a surprise. The one thing I will say is that your users will find a way of using all the resources available to them. And so you better architect limits to those resources from the beginning. If you give them the ability to spin 1,000 Dask workers, they will spin 1,000 Dask workers. So if you don't want them to do that, you have to figure out in advance how to place limits on activities like that. People very quickly become accustomed to computing always being there. The elasticity of this environment is, of course, one of the major draws. But it also means that your services had better be able to do something while they're twiddling their thumbs waiting for new nodes to be added to your autoscale because you have a surge of user demand. I do not want to underestimate the kind of major importance in having management buy-in. Management has to write you a big check to do this, and it's different from the kind of the business as usual norm. And we have been very lucky to have the support of the entire management chain, up to Bob Blum, our director of operations. I will say that I don't think they have regretted it. I think they have. I think they feel they've gotten their money's worth. Some conclusions about doing this for real on such a scale. I think people have heard me rant about how Kubernetes will save astronomy. I will say that having designed those services from the start to be container orchestration based, made a transition to this environment actually totally painless. There are so many benefits in working in a standardized environment that the entire tech sector is working in. There is so much mitigation that you can do for schedule risk by being able to deploy your services early without waiting for infrastructure to be built. It's not cheap, but it is great value for money. I feel that we got what we paid for. The kind of number of services that you have access in that kind of environment is a great age to velocity. Developers love to self-serve. And so, people always ask about vendor lock-in. Actually, vendor lock-in is not an issue. We use extremely standard technologies that are actually available both on other commodity providers and on premises. If you actually choose to build your on-prem facilities that way, it's just very easy to accustom yourself to working in an environment where every time you need something, it is there for you. It's gone so well, we're actually seriously evaluating whether, even for actual operations, it is reasonable to design around a hybrid on-premises Google Cloud model. And I will say that there are many considerations here, institutional consideration, funding model considerations, and so on. But from a technical perspective, the one thing I will tell you is that this was really a no-brainer. There is literally no technical reason not to go down this route, and every reason to do so. And so with that, I will tell you that we are making progress. We are rehearsing, and very soon, hopefully, we'll have our own data and we can look at the sky again, and that's going to be awesome. All right. Thank you very much. Hopefully, I've been busy answering questions on Discord at this point.
Thanks very much, Frosy. I can see you have created some mayhem on Discord. I'm not even sure what questions have been answered or not. I don't think you answered Peter's question yet. So Peter is asking, how long do you keep the original raw data? Can you afford to keep it, assuming Google isn't split up, etc.? Yeah, what happens if Google goes under? Inconceivable, I know.
Yeah. Hi, I'm glad everybody's risen to the challenge. I was just trying to type an answer to that one. So technically, because of the way these projects are funded, we have a commitment to keep the data only for the duration of Ruby operations, which is 10 years. There's actually no, Ruby operations theoretically goes poof at that point. And so that would have been the case whether we were on premises or whether we were on Google. We are, of course, as a project, and I wish the data to go poof after 10 years, and so we are working on various arrangements. I will say that Google is not alone among major providers, that there is a public data set service. So as our data stops being proprietary, we can theoretically host it under the open data set programs that all of these providers have. And of course, also host it to other institutions that want to take it on. Right now, it's like a huge amount of data, but maybe in 10 years' time, it won't seem like that much.
Great. I see a question from Jonathan. I think we have time for one more. Did I hear you mention users spinning up nightmare quantities of Dask threads? And what has your experience been with Dask?
Yeah, so basically a couple of things about Dask. Now, obviously, when requirements were written for this project back in 2012 or whatever, all these things were a glint in people's eyes. We have tried to stay current with what people really expect and anticipate getting user computing, and I think a very Pythonic, highly parallelizable framework that is next to the data, next to the database, like Dask, is clearly a good idea. So we are working on providing that service. We still have some technical arguments about the best model to implement a Dask service. Right now, the kind of a prototype that we're using allows users to actually spin Dask workers within their own Kubernetes namespace, and that's how we're quoting use of the Dask service, because your Kubernetes namespace is quoted, and therefore you can choose whether to actually spin like a very large instance inside that namespace under your quota, or lots of little Dask workers. It's not Dask is not officially offered as part of Data Preview 0, even though our little bright sparks figured out how to use it anyway. But it will be part of future Data Preview releases. And I think a service like Dask is like super compelling, because it's just the parallelization that it offers for very little expertise in how to correctly utilize parallelization. The fact that you can just do it with one notebook line in Jupyter Notebook is actually very compelling at the scale.
Great, thank you very much. I'm afraid we're out of time, so let's continue this discussion on the channel. I must compliment the fact that you brought a Copilot, I see. Let's thank all the speakers again. And now we are almost at the end, so I'm going to hand you over to my POC colleague, Stephen, for a very special event. We see you, Stephen.
All right. Hello, everybody. My name is Stephen Gwynn, and I'm here to present the second annual ADAS Prize for Outstanding Contribution to Astronomical Software. This is a prize we started, I guess, last year, and it's to really recognize the software that has contributed in a meaningful way to astronomy. The way we select the prize is by getting you, the community, the ADAS community, to submit nominations, and then the program organizing committee votes on those nominations. And we want to thank you for your enthusiastic participation. For 2021, the winners of the prize are, the prize is given for IRAF, and specifically it's, well, there was some discussion as to who exactly wrote IRAF. There's an awful lot of people involved, but we narrowed it down to just a core of Doug Toti, Lindsay Davis, and Frank Valdez for developing IRAF. IRAF is a software package that really needs no introduction. It's going to get one anyway. I mean, for many of us, IRAF was our introduction to astronomy software. Developed in the mid-'80s by the folks at NOAO, which is now NORLab, and it's been extended by many other institutions over the years. It's become a standard platform for data reduction and pipeline processing for many, many telescopes, both on the ground and in space. And as a sort of objective measure of IRAF's impact, with doing a bit of bibliometrics, as far as the POC can make out, IRAF has contributed over 25,000 papers. So obviously we can't have everybody give a talk at once, but we've selected Frank Valdez, who's going to give us a talk on to accept this prize. Thank you, Frank. Go for it, Frank.
Thank you, Stephen. On behalf of Doug and Lindsay and myself, I want to thank ADAS for this, what I consider a pretty prestigious award. I want to say that in the future, ADAS should definitely tout its own horn. This is the community that represent astronomical software. My organization is going to put out a press release about this. So I want to thank first the program organizing committee for choosing IRAF, and the larger ADAS community. You out there in the ADAS community are the best to recognize success in our field. I also want to thank the organizations that made this possible. And I'll mention how there have been a lot of challenges over time with this, but there have been a few directors and managers with the vision to keep it alive. And that's Kitt Peak National Observatory, which you see Kitt Peak behind me in this background. So this started with Kitt Peak when it was a separate observatory. Then it became the National Optical Astronomy Observatories, NOAO, for most of its time. And I should also thank the National Science Foundation of the United States for supporting that. And finally, the biggest thanks to the IRF community. We've had many thank yous, and that's what made this particularly satisfying to us. Many thank yous over time as we supported thousands of astronomers with getting the science done. So thank you. Now let me show you some slides. So here's the list of people. Doug Tody, who is often called the father of IRAF, and he is indeed. It was his initial vision that led to IRAF. Then myself, I wrote most or a large fraction of the science applications that astronomers are familiar with. And Lindsay Davis wrote an area of astronomy, as noted here. And I also want to call out Mike Fitzpatrick, who is not listed on the award, but is central to what IRAF is and has been. He did not want to be recognized because he's on the program organizing committee, but he would be the wizard of the IRAF system. Many people have interacted with him as well. There's probably many people who I may miss, but I want to call out a few as some of them are listed here. First, George Jacoby is an interesting point that when we were first developing IRAF, the first person who was asked to make some kind of prototype application on the IRAF system was George Jacoby, and he wrote a very preliminary version of what many people who do spectroscopy will recognize, S-plot. The second line, I want to recognize Jeanette Barnes, who was very active in ADAS and in supporting IRAF as the main contact as a support person. Phil Massey, I've had worked with him to write some documents on how to use IRAF for spectroscopic reductions and CCD reductions. And I've had many people tell me that they learned how to do spectroscopy through reading those cookbooks that Phil, I, and Jeanette put together. There are many others and many groups outside of NOAO that contributed parts of what made IRAF what it is. I give special mention to the SDAS group at Space Telescope, which gave, once they adopted it to replace what they were trying to do earlier, added quite a bit of legitimacy to IRAF. So there are many testimonials, and I put a couple here. Many of you may have written me and said similar things. The first one, that IRAF was the tool to use in his everyday work. I like because it was sent to me by a major director of a major observatory. The other common thing, the refrains that we've heard many times over the years is as other software groups have written software, they often will say, our software is just as good as IRAF, or IRAF's the gold standard that people compare their results against. So all of those testimonials and refrains are very important to us. So I want to start with an anecdote about joining the IRF group in 1982 out of my postdoc at Bell Labs. And so I came and interviewed and talked to Doug about what the vision was. And the thing I love, first of all, the idea of a national observatory that awards time based on the science and was intended to equalize the playing field for astronomers from small institutions with big institutions. Of course, Kitt Peak evolved into NOAO, and we are now Noir Lab. And then I also like the community mission of IRAF. The intent was to provide software for the community. It was not about writing software specifically for some instrument at NOAO, though that was one of the reasons for doing it. The other thing that I found important was at the time in 1982, astronomers who came to Kitt Peak to observe would get their data. And if they wanted to use existing software, they often signed up to be in the basement of our headquarters for periods of time to use mainframe software. And that was the way people analyzed and reduced their data. So the concept of IRAF was one of to get people out of the basement and to be able to use what was now becoming more common, mini computers at their institutions. And then the last thing I loved was the technical vision, as it was explained by Doug, of a virtual machine where IRAF provides the core part of IRAF provides a platform on which everything else is built to insulate the applications from the host, and also providing a system and language that was designed and built for application developers like myself. And in the corner, you see Kitt Peak and NOAO called out with their logos, even though we no longer, well, the Kitt Peak is still an organization, but it's under Noir Lab. The next thing I thought mention was the ADAS, since we're in the ADAS right now. ADAS-1, it was held in Tucson in 1981. And I vividly remember one of our IRAF meetings out on the patio discussing how we could involve more software people outside of our building. And we came up with the concept of holding some kind of conference. And we worked really hard to make sure that it was branded not as an IRAF conference, but a conference for all developers of astronomical systems and software. And Jeanette Barnes, you see outlined there in the first, as one of the editors of the first volume, was pretty instrumental in getting this ADAS-1 in Tucson held. And I do remember people coming from Europe. This was in November, where it's cold in Europe, but we sat around the patio having drinks in our shirt sleeves. So Tucson was a very popular destination for ADASs. We've had more than one ADAS in Tucson. This screen shows some of the papers from that first ADAS. And my first invited talk was on the spectroscopy reduction packages, which are still in use and still fairly heavily used. And this is based on the fact, on the ability of IRAF to be a very portable system. Another paper I contributed to that talk was on optimal extraction for spectroscopy, and that is also still in use. And Doug and Lindsay submitted a paper on digital photometry of digital images, from which most of the digital photometry tools in IRAF evolved through Lindsay's guidance. I show here a bunch of names. It's a very small set of names, but many of you that have been IRAF users will recognize some of them. I just like to comment on a couple. ImExam was written to provide an interface to graphics and an image display. There's a picture at the bottom. And when I wrote this, I was really surprised how widely it became used. I often could find pictures of control rooms, not necessarily at NOAO, that on the screen you could see pictures of ImExam. So it was used at the telescope for measuring point spread functions or getting some coordinates. S-plot I already mentioned for spectral plotting, similar to IMEXAM, and it was used by many people, and that's one that people would say it's just as good as S-plot. And so here you can look at some of the words, and maybe some of them resonate with you. So I mentioned that it was a very innovative project, and you got to remember this is back in 1991. Over the years, many buzzwords have come along, but we have to recognize that some of these things, before they were actually assigned a buzzword, were in the thoughts of Doug and the IRAF group. First was a virtual machine, now common in things like Java. The idea of having a host, an underlying host system that would insulate you from the actual operating system of whatever computer there was. Then the programming language for applications developers, and this was a time where Fortran was dominant, but it was not as good as C, for instance, for developing software. So the programming language that was developed by Doug is based on RAT4, which provided something C-like, but it was compiled into Fortran. We still use the subset preprocessor language, but now it gets interpreted into other languages, but it still remains very portable. And as I mentioned, something like the spectroscopy tools that were written in the 1980s, the code is still usable without change. The important thing for a software developer, an application developer, is the libraries, and IRAF has really got libraries and libraries and libraries aimed for science. One of the areas was the concept of image kernels, so that we started with one image format. When the image formats changed or support was added for, say, real-time runtime fits, the code that had been written did not need to be changed because the libraries provided a kind of protection against that. And something that also is sometimes given as a concern that object-oriented programming became more and more commonly used. What's not realized is that IRAF, and I learned the style from Doug, an object-oriented style, and this was using 1980s Fortran. There have been many successes, obviously, over the years. IRAF has been used by thousands and thousands of astronomers all over the world, and it's still used 40 years after the initial design. I'm counting 1981 when the vision of IRAF started. The first release to the world was in 1986. So I consider we have 40 years of IRAF, and it's still in use. The idea of the virtual machine allowed us to port the virtual machine to many different machines, and I list some here that you may remember from history: the VAXes, Cray, and so forth, and even a fun port by Mike to an iPod. There's also been external packages contributed to IRAF, for instance, the STS-DES suite of tools, Gemini. There have been several other organizations that have written their packages layered on IRAF. That's been a big success for being beyond just NOAO. As I mentioned, IRAF has been used both at telescopes and in offices. At telescopes, not only was it used for evaluating the data, like with IMEXAM, but there was actually a instrument control package developed to run CCDs layered on IRAF. It's still used in a number of pipelines, and it was adopted by many observatories. Now, many have moved on to other developing their own, but again, IRAF is considered an example of where they want to go. And then, of course, the success is the science. So this graphic shows the growth of publications, scientific publications in refereed journals of papers that mention using IRAF. A common phrase would be data was reduced using standard IRAF tools. This graphic goes up to 2015, but it's continued to go up. So that, in my feeling, feeling of our group, is that that is a key measure of the success of IRAF, is that enabling the science. As I mentioned about still being used in pipelines, as well as on people's desktops, here's an example of images from an all-sky, most all-sky survey, the legacy surveys, where the data, the raw data was calibrated by IRAF, and they come from the DECCAM camera on the left and the cameras on top of Kitt Peak, Mosaic and 90 Prime. And they were processed and touched by IRAF at some point in the calibration. Another interesting feature I'd just like to mention is that while most people think of IRAF and the CL as an interactive tool that you run on your desktop, in the pipelines that I've been working with for a while, we run it IRAF in parallel. So we have IRAF sessions that are constantly being created to run modules on a cluster of 40 hosts. And that's how we process the over 1 million DECCAM exposures that we just passed that milestone. So I wanted to talk about the politics and the future. Politics have always been a problem, or a aspect of this, and I'm sure everybody in the audience right now will recognize this, that when you're in a software project, there are a lot of politics going on. For IRAF, from the beginning, there have always been voices wanting to kill IRAF, usually over fairly minor cost rationales. For example, in the very early years of development of IRAF at Kitt Peak and then NOAO, there were voices that said, why should we spend money on IRAF when we can buy more VAX computers? And so the IRAF project, we in the project have had to deal with this constant ideas that money could be saved by eliminating 3 or 4 IRAF programmers, where the amount of money is some 1% of the budget of the organization. Fortunately, as I mentioned, there have been directors that have understood the value and the vision of providing community software. The language that we used, as I said, in the early 1980s was extremely important to us and has proven one of the successes because that code is still unchanged and still runs. But it's always been an argument that we would hear to the point of saying no new software developer is going to want to learn this language. So that has always been a limitation to expanding IRAF. And another common phrase that you may empathize with, some of you, though most people in ADAS are probably more of the, I want to write the software, was that IRAF is a black box, that people could come and reduce their data from raw data to images and papers without really necessarily knowing every detail that goes on, like how a CCD is actually reduced. The thing to keep in mind that I've always had was that there are 2 worlds of people that use our software. There are the power users and the big organizations. And then there's the rest of the astronomers who may not develop software, may not want to write software, want to just get the science, their workplace that have reduced resources. And that's really where IRAF continues to be important. On the question of, or the point about people wanting to kill IRAF, I had to develop, and we all had to develop the thick skin to say the community will vote with their feet. So people will, when people would say, let's stop supporting IRAF, all the IRAF community out there would come forward and say, we still need this. And I'm very grateful for that. Then I'll say a few comments about the future. As apropos to the idea of who actually uses software, over the last 10 years or so, there's certainly been a lot of move to Python and to Jupyter notebooks and all that stuff that you're all familiar with. But the question is, are we going to make everyone write their own reduction analysis code? In this meeting, the only question I asked was along those lines. If a working astronomer wants to do photometry in this particular system, how do they do that? And the answer was basically boiled down to find somebody who used our system to write photometry software. So I think there's still a need for people to recognize that not everybody wants to write their own software to do their basic astronomy. So that leads to the question of, is it possible for there to be any institution that will support general purpose software development? NOAO had that vision, and despite the challenges, kept supporting it to write this general purpose software. CCD proc to reduce CCD images was used on many, many different observatories. But when I look at the world, I don't see that. I don't know how that will ever happen, if there's going to be a next generation IRAF where some organization uses their funding to allow general purpose software that's not specifically devoted to their particular instruments. And then to anticipate a question that I'll probably get is IRAF good for the future? And the answer, in my view, is yes and maybe. Yes, in that IRAF, in its virtual operating system that can be ported, can continue to run with the language unchanged, the code, millions of lines of code unchanged for as long as the host system support the virtual machine. The maybe is that support for it, and also life does move on to new systems. There have been politics about IRAF. Some of you may have thought you heard the rumor that IRAF was dead or IRAF was no longer supported. That's mostly a political thing. So I don't know if IRAF is going to be around in 10 years. I think it will be for some institutions. So that's the best answer I can give you to that question. So again, thank you to ADAS and the IRAF communities. And I show a little humor here of somebody writing a cartoon about IRAF and the challenges people had. A big system always has, it takes a while to learn. And with that, I finish with great appreciation to ADAS and open to whatever you want to do, Stephen.
Thank you very much, Frank. I think we are almost done, but the good news is that there's going to be another ADAS, and I think Stephen is going to tell us about that now.
Certainly try anyway. Just share my screen here. All right. So we're at the end of one ADAS, but another ADAS is coming up in just under a year. I would like to invite you all on behalf of the University of Toronto, and in particular the Dunlap Institute of Astronomy and Astrophysics, and the Canadian Astronomy Data Centre, which is part of the National Research Council of Canada, to come to Victoria next September. Why should you come to Victoria? Well, Victoria is one of the most spectacular places on the planet. I have lived in the south of France. It's okay. I've worked in Hawaii. It's okay too. But Victoria really is one of the nicest places to be. And if we go for the sort of hybrid model that we've been using here in South Africa, you will have the afternoons free to explore it. The venue is right next to the water on one side and about 15, 20 minutes walk from the beach that's shown on the right here. These pictures that I'm showing you, some of them are taken from stock photography, professional photographers. Some of them are just taken with my phone. It really is one of the most beautiful places to be, with a large collection of wildlife. So here, this shows you some of the whales. And if you do have the afternoons free, you can take either those two boats to go whale watching. The guys on the left guarantee that you'll see whales. The guys on the right don't guarantee guarantee that you see whales, but do guarantee that they'll put up some white flappy things. Or maybe you won't need to, because like every so often the whales come into the inner harbor of Victoria and you can see them for free. You may not just see whales, there's also a wide variety of other wildlife, and in particular starting to be overrun by the deer on the lower right there. Victoria has excellent food, in particular seafood and in particular salmon. I'm just going to show you two of my favorite restaurants. This one here is sort of the high-end, maybe once a year restaurant, which serves an excellent grilled salmon, waterfront dining. Then there's also this food truck on the dock that also produces excellent grilled salmon with also waterfront view. The no astronomy conference talk would be complete without mentioning the fine alcohol available at the prospective venue. Victoria is no exception. We have an extensive craft cocktail scene. We have several distillers that have sputtered up in the last few years. The gentleman on the left there is responsible for a significant fraction of the liver damage I have suffered over the last few years. And it's not just distillers, there's also breweries. We have about 15 or so brew pubs and breweries that have come up, including some that have just been started up during the pandemic. And I should point out that there is not one, but two local beers that are inspired by the local telescope. The drinking can start as soon as you land in Victoria's International Airport. There is a brew pub and a distiller on the premise on the far side of security. So it can be the first thing you do when you land and the last thing you do just before you leave. I should point out that it's not just hard alcohol and beer that's available. We have wines that are comparable to the finest French and Italian wines. In fact, they are the finest French and Italian wines. It turns out the French and Italians ship. Besides booze, there's also a plethora of really nice, really fun coffee shops and tea rooms in Victoria. So that if you don't need depressants and you prefer stimulants, you will be served. But the main reason you should come to Victoria is because of the people. So this conference has been fun. This conference has been productive, but it's not the same as being in person. So this is a shot from the conference photo from the last in-person ADAS. And I sort of have two reactions looking at it. One is, why aren't these people wearing masks? Why aren't they more spread out? But the other reaction I have looking at this picture is, everybody looks happy. Everybody, and the barrier, although there's a discussion going on in the feedback channel about Discord versus GatherTown for communication, the best interface, without question, is just talking to people in person. So I don't know what next year is going to look like. It may be that the Delta variant morphs into, the Omega variant, and we're in front of our screens like we are now, or most of us are now, or not. I'm really hoping that we will meet next year in Victoria in person. Thank you very much. I would also like to say at this point, that we should really thank the organizers of this year's ADAS, who have done an absolutely marvelous job under very trying circumstances.
It's not on. Now it's on. All right, well, that's kind of feels like it's over far too quickly. So I'm a little bit sad. I'm also more than a little bit relieved, because this has been quite a scary experience for us organizers in very many ways. So speaking of which, has anyone tested COVID positive this week? Okay, good. So if you do plan to test positive, can we please ask you to get out of town first? Anyway, never mind the pandemic, like this whole idea of a hybrid meeting has been pretty scary to begin with, because none of us actually had any idea how to do a hybrid meeting when this whole thing started. Like, we all remember normal meetings, we're all used to Zoom webinars by now, but how do we combine the two? That just seemed a complete mystery. Well, I've got the secret formula now. I figured it out, and I'm going to share it with you. So the secret formula is you get some very competent people to do it for you, and you go and have a beer in a bar. And so, first of all, I would like to thank these extremely competent people. So Samir's team and Ruby, the Ghost in a Machine, would you please step out from the shadows for once? Or at least speak, show your faces. The problem is if they abandon their workstations, then the broadcast interrupts, so it's kind of a chicken and egg thing. Anyway, thanks a lot. I mean, you've made this meeting run, and, well, the rest of us pretty much just had to show up and talk, right? I would also like to thank my colleagues on LOC, particularly those that did the tech heavy lifting. So we've got Benjamin over there, who was the sheriff of Gathertown, and I have to tell you that he is going to be the sheriff of the proceedings next. So you'd better send in your submissions on time. Do not underestimate the persistence of an Afrikaans person, because he will be coming after you, and he can call in a Russian for backup. So your proceeding will be on time. But also, of course, Athanasius, Carolina, Nikki most of all. Well, we've already thanked Nikki, but I think we can thank Nikki again for suffering through all this. But I mean, you guys really pulled through in all the technical and admin preparations here, and, you know, with a team like that, organizing the meeting was actually seemed easy. And to us, of course, because you got this whole show on the road in the first place. You know, it wouldn't have happened without you. But of course, the other scary thing is, could we actually throw an in-person meeting, and what if nobody turned up? And here what I'd like to do is to really recognize the South African astronomy community. Because I remember having a conversation about ADAS with Russ way back, and this was like, I think we were in the middle of the second wave, vaccinations hadn't even started. Could we even contemplate some kind of an in-person meeting, and would anyone show? And then we thought, well, actually our community is big enough that we can just run ahead with it and trust that there's enough South Africans for whom this meeting will be valuable. And, you know, in the time that the two of us have been here, this country has really turned into an astronomy superpower, and that's absolutely fantastic to see. And then, fortunately, other people did turn up. So I'd like to say thanks to our international visitors, the Russian delegation in particular. But not just them. I mean, we have people here from remote, exotic, and inaccessible locations, such as Western Europe. Thanks a lot for turning up. I mean, it must have been a complete leap in the dark to commit to an in-person meeting in South Africa during a pandemic, but you did that, and you know, I'm very glad you did it, and I hope you're glad you came. Thanks a lot to all the remote participants and the speakers, and I'm very sorry you didn't come in person, but a big thank you for connecting to us at all these odd time slots and making this conference such a lively event. I checked, we had something like 5,000 messages on the Discord server, so that's like well over 10 per person at least. So yeah, you guys have been busy, and this is great. Big thanks to the program organizing committee for backing me and Russ up with this crazy idea of a hybrid meeting. Like I said, second wave, no vaccination. It seemed completely nuts to plan something like this, but the POC backed us and gave us the security and the commitment that we needed to actually run with this. And lo and behold, I think this has actually worked. So we had about 370 participants in total. I don't remember exactly, it might be slightly less than Granada, which was fully virtual, but it's certainly way, way more than any in-person ADAS has ever been. And, clearly this meeting format is here to stay. What with the climate emergency, we all have to get quite a bit pickier about our travel. Sometimes there's no substitute for face-to-face time, but, being able to reach out and to engage 400 people in a meeting like this is, especially students who could never afford to travel very much at the best of times, like especially all the students we've managed to reach. This is, it just seems like a no-brainer having this format for the future. Of course, we're all improvising, so this is why you might have seen on Discord we've started a feedback channel and a feedback mailbox. So do please send us feedback, what could be done better, if you have different ideas for how to do this. And the LOC of the next conference is also going to appreciate that quite a lot. So speaking of experiments, I would like to commend the people who weren't afraid to push boundaries and exploited this new format to the hilt. So in particular on Sunday, we had two great tutorials on Carta and GNU Astro, and I say they were great not just because of the technical content, but because of the way it was done. There was a primary speaker, and there were co-pilots on Discord who were, doing everything to push the discussion along and keep things lively. And that was great to see. And then, of course, we had Michelle Ntampaka's talk on Tuesday. And that was a riot. She was her own co-pilot, right? She did the recording, she was her own co-pilot, she was the one who showed us the horse. And it was just utter mayhem for 15 minutes. The most fun talk of the conference. I felt mildly sorry for Roger who had to chair that. It must have been a little bit like riding a wild horse, but a lot of fun. So if you missed it, please go to the recordings and see it and scroll back in the Discord channel. You'll see what was going on. And Frosty actually just now got something similar going, right? I think a bit less horseplay, but also a lot of fun. But more scientifically, to me, the other highlight is how much ADAS has become. It's not even software and systems, right? It's more of a conference about solutions, technologies, and ideas. And I mentioned in my opening remarks that my first ADAS was ADAS 2. And, back then, software was just kind of this novel growing thing that some astronomers got into because they found it interesting. And now, of course, it's something that no astronomer can do anything without. Back then, it was very novel to have an astronomy software conference. And as Frank just mentioned, there was actually, informally, the first ADAS was called the IRAF meeting, and unfortunately, they decided to give a more inclusive name. But the fact that it was actually informally called the IRAF meeting is actually testimony of how deserved this year's software prize was. But anyway, a few years passed, and suddenly everybody's doing software, and then ADAS, to me, suddenly had a kind of a Tower of Babel feel. And, maybe that was a reflection of my narrow horizons at the time, but it felt like everyone was doing software, but I would listen to an optical software talk and I would not see what I get out of it for my radio interests and vice versa. So it kind of felt like that for a bit. But now in these last few years, something really wonderful has happened because suddenly this whole thing is, again, very coherent. And I think that's because it's become more about technologies and solutions that cut across all branches of astronomy. And we saw it this year, particularly with machine learning. But we've also heard a lot about containerization, workflow management, things like Jupyter, browser-based visualization, Dask, the cloud. Like everyone is adopting these solutions regardless of their branch, and this sharing of experience is fantastic to see. So I think this is all very exciting. This is really the engine room of astronomy, I think. And to all the students listening, I can say, you know, I cannot think of a more interesting or useful thing to be doing right now than astronomy software, really. So if you're here, you're definitely in the right place. And with that, well, I'm looking forward to the next ADAS. Certainly looking forward to not having to organize it. But yeah, see you in Victoria, live or online. This one is done. Let's go to the bar. Meeting closed.